this first idea, the insertion method, this is useful when you're trying to work out arrangements, but you've got certain objects that are not allowed to be together. Okay? So this is one of the questions which might have been in the text, I'm not sure. There was one similar to this anyway. So letters of the word between arranged in a line, how many ways can they be arranged if, say, all the E's are separators? Okay. So the way possibly people do it, the traditional way of doing it is go, alright, look after the condition first, how many ways can I place the E's? So there's all the spots I can put it. I could put the E's there, or I could put the last one there, or I could change it to there. So there are all the possibilities when E is in the first and the third spot, then the third E could go in the last three. Say I put them in those spots, then there would be 2. There's another possibility, and of course there's another 2 possibilities. Another possibility, and I keep sliding that first E along. There's another possibility. All up, there's 10 different ways I could place the E's. Then I arrange the other letters. So there's another 4 letters to arrange 4 factorial, and we get 240. And that's probably the traditional way people approach it. The insertion idea is to do it a little bit differently. Actually, we're going to place the unrestricted objects first. So the B, T and the W and the N. So let's say, for instance, that's how I arranged it. And you'll notice I've left gaps in between each of them, because I now have to place the E's. But basically, if I'm going to ensure that the E's are not next to each other, then I've just got to place an E in the gaps. And then there'll always be a letter either side. So 4 factorial for the B, T, W and the N. And then I've got 5 spaces, because it could be at the end as well, remember? It doesn't necessarily have to be in the middle. So of those 5 spaces, I'm just going to select, how many E's did I have? 3 E's. So it's a combination. Order's not important because they're all E's. So 5C3, there's my 240. So that's what's called the insertion method. What about if exactly 2 of the E's are together? Well, if exactly 2 of the E's are together, again, I can arrange the B, T, the W and the N. But this time, instead of saying I've got 3 E's to place, I've got 2 objects to place. One of those objects is a double E. So somewhere I'm going to put 2 E's in one of those spots to ensure 2 of the E's are together. And in another one of those spots, I'm going to put a single E. So this time the order would be important because the double E and the single E could swap round. So it'll become a permutation. So of those spots, I'm going to use 2 of them. So 5P2. And so that would be 480 ways of doing it. Okay, another idea is what we call using separators. So that's when you've got large groups and you want to divide them into smaller groups. So here's a question. We've got 3 pirates and they've got a treasure chest full of gold. There's 48 gold coins in there, but unfortunately there's also 2 lead coins. So the first pirate is going to keep taking out gold coins until he gets a lead one. And once he picks up a lead one, that's it, he's done. That's all the gold he gets. So then the second pirate comes along and it's his turn. And he can keep pulling out gold coins until he gets the next lead coin, and then he has to stop, and then the third pirate gets whatever's left in the chest. So how many ways can these coins be distributed? So really, if we think of the coins as letters, and the lead coins I'm going to call them L's, the gold coins I'll call them G's. So really, it's just like saying how many ways could I arrange 2 L's and 48 G's. So the L's, if you like, are separating the groups of the gold that the pirates are going to get. So we know that to be 50 factorial on 48 factorial 2 factorial, 1,225. I suppose another way I could have thought about that is I could have said, well, there's 50 coins all up, 2 of them are going to end up being lead coins. So from the 50, I'm going to choose 2 of those coins to be lead. 50C2, which is also 50 factorial on 48 factorial 2 factorial. That's another way I could have thought about that. Here's an actual one from an HSC. It was an extension 2 HSC question. So this time we've got 10 identical coins and they've got to go into 4 different boxes. How many ways can we do it? Okay. So a similar idea, I'm going to say I've got 10 coins, but I'm going to have 3 S's. And the S's, if you like, are going to be when the next box starts and so on. So unlike the last one where I had 2 lead coins which told me when I was going to start the other one, I'm just going to call it an S for, or if you like, stop, put it into the next box, or separator, whatever you want the S to stand for. So I'm going to make it 3 S's and 10 coins. So same sort of idea as the last one. So 13 factorial, 3 factorial, 10 factorial, 286 ways of doing it. By the way, when that question was asked back in 2012, only 1% of the state got it correct. 1% of the state. And which gives you an idea of how tricky some of these tend to be. Let's have a look at 2013 one. A hostel's got 4 vacant rooms. Each room can accommodate a maximum of 4 people. How many ways can 6 people be accommodated in the 4 rooms? I'm just going to work out how many ways, if there was no restriction. If there was no restriction, then it becomes a basic counting idea. So it's 4 to the power of 6. Because basically each person has got a choice of 4 rooms. So we'd end up with 4 times 4 times 4 and so on. Okay. Now, I want to take away all the ones where there's 6 in a room. Because they've said there's a maximum of 4. So in all those possibilities we just worked out, we've got a possibility where all 6 are in one room. I don't want those. So I'm going to take those away. So 4C1, that's going to be which of the rooms will have the 6 people. There's 4 different ways. And I suppose that's logical. Either the first room would, the second room would, and so on. But also we can't have 5 in a room. So I'm going to take that one away as well. So I'm going to choose 4C1. I'm going to choose which room's going to have 5 in it. 6C5. Then I'm going to choose which 5 are going in that room. And then that final person who's been left by themselves has got a choice of 3 rooms they could go in. Well, that leaves me with 72. That, therefore, should leave me with all the possibilities where there's a maximum of 4 in a room. So 4,096 minus 4 minus 72, 4,020. Now, that wasn't using a separator idea or an insertion. Why did I bring that one up? 15% got this correct, so it was better than the last one. There was only one problem. It was a multiple choice question. And you'd think with a multiple choice question you'd be expecting at least 25% would get it right. When you got thousands of people, if they just randomly guessed and you had thousands of people, you'd expect about 25% getting it right. So because they weren't randomly guessing, because they're having a go at it, only 15% got it right. That gives you an idea of how tricky that particular one was that year. Another thing that combinations can be used for, and you've been using it without realising it, and that's expanding perfect parentheses. What do I mean by perfect parentheses? I mean perfect squares, perfect cubes, and so on. Okay, so that one, a plus b squared equals a squared plus 2ab plus b squared, you actually have been using combinations without realising it. Because if you think about how you expand, now a plus b squared is really a plus b times a plus b. And what you're doing is you're taking one pronumeral from one parenthesis and you're multiplying it by another pronumeral in the other parenthesis, coming up with a new term made up of 2 pronumerals. Might be a times a, might be a times b, might be b times b. So what are all the different ways we could get the a and the b? So I know, as I say, I could get a times a, I could get b times b, I could also get a times b. Well, how many ways could I select 2 a's? There's only one way I could do it. Take 1 from the first one, 1 from the second one. And the same with the 2 b's. Well, how about the ab? Well, it would be 2 factorial. So let's expand that idea out. If I've got a plus b plus c plus all the way up to n squared, then we should now logically be able to expand that out, because in each one of those I'm going to have two parentheses. I'm going to take one pronumeral. So there's one way I could get a squared, there's one way I could get b squared, there's one way I could get c squared, and so on. But there's only two ways I could get two together, ab, ac, and so on. So any perfect square, no matter how many pronumerals you got in there, is going to be the pronumerals themselves squared plus twice every possible combination of two letters that are in there. That'll be everything to a perfect square. Well, what about a perfect cube? Same idea. I've only got a and b, but this time I've got a plus b times a plus b times a plus b. What are the different things we could have? We could have three a's. I could have three b's, so they're going to have the same chance. The second one, I've got one a and two b's, which would be the same as one b and two a's, and that's pretty much it. That's all I could have. So the question is, how many ways can each of those things happen? Well, the three a's and the three b's, again, there's only one way I could do it. An a from the first one, an a from the second one, an a from the third one. But the question is, how many ways can I grab two a's and one b? Or how many ways could I arrange two a's and one b, if you like? 3 factorial divided by 2 factorial. It's no different to saying how many words can I form using two a's and a b. So that would be the coefficient of the ab squared in our expansion. And if you remember, that is correct, because if you remember your perfect cube, it does go 3ab squared plus 3. Yeah. So again, I could grab anything, a plus b plus c all cubed. It's going to be a little bit different this time, because now I've got a possibility of getting a, b, c. There's still only going to be one way of getting a cubed, b cubed or c cubed. There's still going to be 3 factorial and 2 factorial ways of getting the a squared b and so on. But how many ways could I get a, b, c? Not necessarily in that order. And that would be 3 factorial. So that would be the coefficient of ABC. So there's our expansion for a plus b plus c all cubed. And again, you could do that to as many pronumerals as you like. Alright, well, let's have a bit of fun. Let's do power of 4 then. What are all the things we could have? We could have a times a times a times a. So the same pronumeral 4 times. I could have one pronumeral 3 times and the other one once. Or I could have both of them twice. So the coefficient for a4 plus b4 must be 1. How many words could I form with 1a, 3 b's? Well, 4 factorial on 3 factorial. How many words could I form with 2 a's, 2 b's? 4 factorial on 2 factorial, 2 factorial. They should be the coefficients of each of those. I'd have one lot of a6, b6, c6, d6. Then I could have 5 of one and 1 of the other, 6 factorial and 5 factorial. I could have 4 of one, 2 of the other, 6 factorial, 3 factorial, 2 factorial. I could have 3 of each, 6 factorial and 3 factorial, 3 factorial. And I could have 1 oh yeah, I could have 1 4 times, 1 b and 1 c. Oh, actually, I could also have 3 of one, 2 of one, 1 of the other. Is that every possibility? Oh, no, because I could also have 2 of each one. Oh, what one did I forget there? Oh, I've forgotten 3 of one and 1 of each of the others. Oh my goodness. There's your expansion for a plus b plus c plus d, all to the power of 6. There's another one. Oh, you're right. Look at that. A squared, b squared, c, d. So there's your expansion. All I'm saying is theoretically you could do that. Don't panic. I don't think I'll ask that one in the test. But look, it's another use of permutations, combinations that perhaps you wouldn't have thought of. All right.